script B, any collection of closed balls in Rn, in a metric space X, so X is any metric space. And with just one condition, that the soup of the diameters should be finite. That's the only restriction. Then there exists a pairwise disjoint subcollection B prime contained in B such that the union of all the balls in B, that's the original collection, is contained in the union of the balls in the pairwise disjoint collection, except that you've got to enlarge each of those by a factor of 5. So here we're using the notation that I mentioned last time, that if B equals B rho X, closed ball center X and radius rho, then B hat means the 5 times enlargement. In fact, you can actually say a bit more here, and it's actually useful to do that because it gives a hint about how the proof goes. In fact, you can actually make this a bit more precise. In fact, for every B in B, in the original collection, there exists some ball B primed in B primed with B intersect B prime non-empty. Well, let me just say it this way, actually. Well, yeah, let's say that. Non-empty, and in fact, B contained in the 5 times enlargement of that particular ball. So the claim, in fact, the claim is that we can find such a B prime so that this is true. This is the key property. Picture looks something like this. For every ball B in the original collection, the claim is that you can find this collection such that for every ball in the original collection, there's one of the balls in the pairwise disjoint collection. Let's call this B prime. Yeah, here it is. It's one of the balls in the pairwise disjoint collection such that the 5 times enlargement, so we've got to enlarge this by a factor of 5. So that's the picture. Claim is that you can find a pairwise disjoint collection like that. So let's give the proof. I think I started the proof last time. We let R be this quantity. Let's call this soup. Let's call that R. It's a real number, finite. And then we can write Bj. So we break B up into countable collection, countable subcollection, such that the radius, such that the diameter, so Bj is the set of balls in the original collection, such that the diameter of B is bigger than R over 2 to the j and less than or equal to R over 2 to the j minus 1. J equals 1, 2, etc. Notice that then, of course, it's true that, notice this takes care of all possibilities for the diameter. So that's certainly true that B is the disjoint union, j equals 1 to infinity of bj. So that's a way of breaking up the original collection. Now, the proof starts by taking, let b1 prime, this is j equals 1, let b1 prime be a maximal pairwise disjoint. Subcollection of b1. Remember that, as we discussed last time, by Zorn's lemma, which is one of the equivalents of the axiom of choice, you can always find such a maximal subcollection, pairwise disjoint. Oh, pairwise disjoint subcollection. There it is. So do that first, and then we're going to proceed inductively. Assume that j is bigger than or equal to 2, and b1 prime up to bj minus 1 prime are already chosen. Then we've got to say, to make the inductive definition complete, I've got to say how we're going to choose bj prime, right? So, and let bj prime be a maximal pairwise disjoint. Subcollection. Now, you might be tempted to say, well, let's just do the same thing that we did here. Just take a maximal pairwise disjoint subcollection of bj. That would be the analog of what we did at step 1 here. But we want to make sure that we get pairwise disjoint balls. So we've got to make sure that we're choosing balls at this jth step which are disjoint from the balls that have already been chosen. That's important. So we take a disjoint subcollection of the set of balls that have already been chosen. So that's the balls bj minus the balls that have already been chosen. I equals 1 up to j minus 1, b sub I prime. So that's sort of a slight subtlety there. You've got to make sure that you, at the jth step, you pick balls that are disjoint from the ones that you've already chosen. And that's it. Then you let b prime be the union of all of these. bj prime. And the claim is that that has this property. So let's check. Let's call this property star. So the claim is that star holds. So let's check that. So check. Well, let's see. Take any ball. What we've got to do is take any ball in B. So let B in B. Well, if B's in B, it's in one of the BJs. So remember, the BJs exhaust all of that. So let B be in BJ. Then we must have, here's the key point, we must have that B intersect B prime is non-empty for some B in Bj prime, for some B in Bj prime and the previous guys. So for some B in the union of the Bi primes ranging from I equals 1 up to J. Now why is that? Well, you see, otherwise we could just append B to this collection Bj prime. Otherwise, Bj prime union B. See, we could append it to that collection, get a bigger collection. Would be pairwise disjoint then. If B intersect B prime is empty for every for some B prime in that. See, if that's empty for every B prime, then that means that this is a pairwise disjoint collection. Pairwise disjoint collection with B intersect the union from I equals B intersect C empty for every C in the union I equals 1 up to J minus 1. Bi prime. And you see that's a contradiction. That contradicts the maximality. Then we've got a larger collection that satisfies all the conditions that we had on the maximal collection. So that's the end of the proof. Or not quite the end of the proof. That at least says that we've checked this. So this is correct. That's correct. Now let's check that does mean star here. Well, B intersect B prime is non-empty. What does that mean about the diameters? Well, the diameter of B prime, let's see, the diameter of B is diameter of B is in Bj, so the diameter of B is between r over 2 to the j minus 1 and r over 2 to the j, right, by definition. So the diameter of B is less than or equal to r over 2 to the j minus 1, whereas the diameter of B prime is bigger than or equal to r over, let's see, what's the worst that could be? So the worst that could be would be r over 2 to the j, because B prime, we're talking about B prime in this collection here. And the smallest radius that appears here is the number r over 2 to the j. So diameter of B prime is bigger than or equal to at least a half this guy. Half the diameter of B. So then the picture of that would be this. Here's B prime. It's intersecting B, and B prime has at least half, well, that's a bit generous. So what's the worst case that could happen? The worst case is that you could have just half the radius. So the worst case picture would be this. B prime is half the radius of B. So that would be sort of the worst case picture, and this distance would be half that distance. Now think about that. If B prime is at least half that radius, if you enlarge, let's count. 1, and this is then, yeah, right. If you count, you see this would be, the worst case is that's 1, 2, 3, 4, 5, right? So the 5 times enlargement contains that. So indeed, we have this. So that's the proof of the 5 times covering lemma. Very nice thing. So let's talk about one important corollary of that. It's called the Vitali lemma. And in order to state this, I've got to introduce one more bit of notation. Let me introduce that here. Suppose we take a set A contained in the metric space, then a definition, we say that a collection script B of closed balls covers A finally, if for every x in A, for every x in A, the inf of the set of balls in B, such that set of diameters of balls in B rather, sorry. So you look at diameters of balls in B which contain X. So you look at the infimum of all those balls. You look at all the balls in the collection which contain the point X. That should be 0. So that simply means that the picture's this. That you've got this covering of A by, here's A. You've got this covering of A by balls. And you've got to have the property that at each point X, there are arbitrarily small balls in the collection containing that point X. Right? So that's what you mean by covers A finally. And that's what this Vitali lemma is about. So suppose A is contained in X. And script B is any collection of closed balls which covers A finally. Then you can find a pairwise disjoint subcollection of this collection of balls. Yeah, I forgot to say, for every, no, that's right, that's the definition. Then there exists a pairwise disjoint subcollection, script B contained in B, such that if you take A minus the union of any finite collection out of this pairwise disjoint collection, so you take, say, finitely many balls, B1 up to Bn, out of this pairwise disjoint collection, then the claim is that you can pick B prime so that this is always contained in the 5 times enlargements of the remaining balls in the pairwise disjoint collection. Sounds sort of weird at first. So this is contained in the union B prime hat such that B prime is in B prime minus B1 up to Bn. And the claim is that you can do this for every finite collection, B1, Bn, contained in B prime. So whenever you take a finite collection out of B prime and you subtract that off the set A, then what's left after you subtract that off from the set A is contained in the 5 times enlargements of the remaining balls in B prime. So let's give the proof of this. It follows directly from this 5 times covering lemma. So proof. Okay, so now we'd like to apply the 5 times covering lemma, but you always have to be careful about that because remember there is one condition about that you have to check to apply the 5 times covering lemma, and that's this condition. That's finite. Now in this case that doesn't matter because we can assume that the diameter of B is less than or equal to 1, say, for every B in B. Because after all, the collection, these balls cover finally. That means there are small balls of arbitrarily small radius containing any given point. So certainly balls of radius less than 1 containing any given point. So you might as well throw the other balls away. You're not interested in those. So then we can just use the ball. So let's assume that. Simplifies the discussion, simplifies the notation. So let's assume that we already have that. Now we can apply the 5 times covering lemma. So choose pairwise disjoint. I'm going to use this abbreviation again. Pairwise disjoint, PWD. Choose pairwise disjoint collection B prime contained in B such that this condition star holds. And let B1 up to Bn be any finite subcollection in B prime. Now observe that X minus the union, see this is a finite union of closed balls. So this is a closed set, finite union of closed sets is closed. So that's a closed set, so that means this is an open. That's the key point. So that's open. So that means if you take a point X in A minus this union, so if X is in A minus the union, J equals 1 up to N, Bj, then there's some ball, there exists a B in B, in the original collection, with B intersect the union, J equals 1 up to N of Bj empty. Because remember that this collection covers finely, so that means there are arbitrarily small balls centered at X, and since this is a relatively open set, this complement is open, so that means you can certainly pick a ball containing X which misses all of these balls, so you get this. But now we've got this property star on the other hand, so we can apply that. So, but by star, there exists B prime in the pairwise disjoint collection with B intersect B prime non-empty and B contained in B hat. That's just what star says. But you see, that means that none of these B primes here can be Bj because they don't intersect, right? So thus B prime not equal to Bj for every j equals 1 up to N. And that's it. That means we've shown that that any point in this is contained in the union of the 5 times enlargements of all the balls other than these given collection B1 up to Bn. Okay, so that's the Vitali lemma. Now I want to come back to the main theorem that I talked about last time about densities, the upper density theorem. So we need a couple more things before we can give the proof of that. One of the things we need is this Vitali lemma. Another thing we need is a bit of new notation, which we haven't introduced so far. So let me tell you about that. So this is just notation, but it's important notation. So mu, any outer measure, any Borel regular, or any, to begin with, any outer measure, generally first, any outer measure on a space X. For the moment, it's completely abstract. And you take A to be any subset of X. Then you get a new outer measure. You can define a new outer measure simply by, it's called mu restricted to A. It's sort of a right angle symbol. Mu restricted to A. And I've got to say what it does to sets. I want to say what it does to any subset. So for any subset Y, this is defined to be mu of A intersect Y. So you get this, and clearly it's very easy to check that this is an outer measure. So exercise. Mu restricted to A is an outer measure. On X. And it's got some nice properties. One property that's completely a little bit surprising but trivial proof is that any set which is already mu measurable is automatically mu restricted to A measurable also. Doesn't matter whether A is measurable or not. So claim, if you take a set Y is mu measurable, then Y is also mu restricted to A measurable. A doesn't have to be measurable for that to be true. So at first sight that sounds a little strange, but the proof is easy enough. So let's check that. So check. So we remember how we check that things are measurable. That's the Curry-Theodori requirement. So we've got to take an arbitrary set S and check that Y cuts this measure additively. It cuts any other set additively. So S contained in X. Let's look at mu restricted to A. Y, we've got to show that mu restricted to A S. We've got to show that S is going to be cut additively by Y. Mu restricted to A additively by Y. Well, let's check it. First of all, by definition, this is just this. Mu S intersect A. Well, let's write it as A intersect S. And then by the mu measurability of Y, by the Curry-Theodori definition, that's the same as mu A intersect S intersect Y plus mu A intersect S minus Y. By the mu measurability of Y. And notice that's exactly, if you stare at this for a bit, this is exactly the same as mu restricted to A of S intersect Y plus mu restricted to A of S minus Y. So that's it. It's very easy proof, but sort of surprising. Now there's one little trap here that you mustn't fall into, and that is if you do this starting with a Borel regular measure, it is not necessarily true that mu restricted to A is Borel regular. All Borel sets would be measurable by this result, right? So if you start off with a Borel regular measure, it's certainly true that all Borel sets are measurable by this fact. But it's not necessarily true that the other property of Borel regular measures holds. That is, remember the second property of Borel regular measures, you've got to be able to check that given any set A, you can find a Borel set containing A with the same measure. And that's not necessarily true unless you make additional assumptions about A. So let me make that, and let me tell you what that condition is. So note, mu Borel regular on a topological space X does not imply, in general, that mu restricted to A is Borel regular. Let's see here, yeah, mu restricted to A. However, this is okay provided two things are true. Okay, provided the measure of A is finite and A is mu measurable. So you may want to think about the proof of that. If you get stuck, you'll find there's just a couple of lines of argument to check that. But think about that, see if you can come up with the proof yourself. If you get stuck, you'll see it's in the text. So exercise. Check this. Oh, while I'm on the subject of exercises, I forgot, didn't I? I should tell you what the week 2 problems are now, before we continue. Well, I'll do that at the beginning of the next hour. So, okay. So that's a bit of mu notation. This is very convenient notation. Notice I was calling this mu restricted to A, but that's not really literally correct, is it? Mu is still an outer measure on the whole space X. You're not restricting everything to being contained in the set A, so it's not really the right terminology, but people use that terminology anyway. What mu restricted to A does, it does apply to all possible subsets of X, but notice it measures everything outside A as 0, right? That's the point. Measures everything outside the set A as 0, because you take mu of A intersect Y, which is empty if Y is in the complement of A. So yeah, by all means, call it U restricted to Y, mu restricted to A, but remember, it's not quite literally that. Okay, so now let's start our proof of the upper density theorem. The main tool, other than this Vitali lemma, is this so-called comparison lemma. So let me explain that. So comparison lemma. So here, mu, so X is a metric space. And mu, any outer measure with such that all Borel sets are measurable. So a Borel regular measure, for example, would be fine, such that all Borel sets are measurable. And take two subsets of A. Take A1 contained in A2 contained in X. And assume that, assume that A1's contained in A2 contained in X, and the upper density, the upper n-dimensional density of mu A2 X is bigger than or equal to T for every, bigger than or equal to T for every X in A1. Remember, this guy is lim sup. As rho goes down to 0 of the measure of A2 intersect with the ball. divided by the measure of the standard Euclidean ball, the Lebesgue measure of the standard Euclidean ball. So that's that guy. And assume that, so here t is given, so t bigger than or equal to 0 given. Then the claim is that this implies then t times the n-dimensional Hausdorff measure of the set A1 is less than or equal to the mu measure of the set A2, which is not at all completely obvious. But if you sort of look at these ratios, so this says that asymptotically mu A intersect B2 is bigger than or equal to t times this term. So that sort of gives you a hint about, a very small hint about why this might be true, but that's all. So let's see if we can actually prove this. Then you'll get a much better idea why this turns out to be true. So let's give the proof. Oh, one important thing to note here. Notice that there's no assumption here on A1 and A2 being mu measurable. That's rather important in the applications because A1 and A2 in many applications arise in a rather strange way, and there's no possibility of checking that they're measurable, or at least no easy possibility of finding that they're measurable. So it's important that you don't need to assume that here. You can still apply this comparison lemma. So let's look at the proof. So first thing to notice is that without loss of generality, we can assume that t is actually strictly positive, and also that mu A2 is finite. You see, that's clear, isn't it? Because otherwise these are trivially true. If t is 0, then this side is 0, and of course that inequality is trivially true. And likewise, if mu A2 is infinity, then of course this is true, trivially. Everything's less than or equal to infinity. So no problem in assuming those. Okay, so let's assume those. And then we're going to try to use this Vitali lemma. So we've got to come up with a suitable collection of closed balls. Well, we're going to use this definition that this lim sup is bigger than or equal to t. So pick some tau between 0 and t. So just give yourself a bit of breathing space, so just a bit less than t. And then lim sup, we're given that lim sup as rho goes down to 0, we're given that this is strictly bigger than tau. It's bigger than or equal to t, so it's strictly bigger than tau. So mu A2 intersect B rho x over omega n, rho to the n, is strictly bigger than tau for every x in A1. That's what we're given. Now, well, because of that, there's certainly a sequence of rows going down to 0 where this is true. So it seems reasonable then to use these balls as our collection of closed balls. So let script B be the collection of balls, closed balls, B rho x, such that mu A2 intersect B rho x is strictly bigger than tau times omega n times rho to the n. And now, clearly, that set, closed balls x, with x in the given set A1. So we're looking at all these balls, exactly looking at these balls. So that seems like the natural collection of closed balls to look at. And notice that collection does cover A1 finely, because actually lim rho tends to 0. So there are balls of arbitrarily small radius, even centered at X, which satisfy this inequality. So trivially, this covers A1 finely. So then B covers A1 finely. Hence, we can apply the Vitali lemma. Hence, by Vitali implies that there exists a pairwise disjoint subcollection B prime contained in B with this inequality holding for every finite collection. Let's call it double star so we don't confuse it with the thing I had called star before. So pairwise disjoint B with star, double star holding. Okay, so what can we do with that? So let's check that. First thing to observe is that just using the pairwise disjointness, notice that if you take any B1, Bn in this pairwise disjoint collection, then the sum J equals 1 up to n of mu A2 intersect Bj. Well, let's see. These are pairwise disjoints. So mu A2 intersect Bj is the same as the mu of A2 intersect the union J equals 1 up to n Bj, because they're pairwise disjoint. By the way, there's a subtlety here. Notice we're not assuming that A2 is measurable. But nevertheless, one of the things we proved about measurable sets without a measure, notice these Bj's are measurable, of course, because they're Borel sets. One of the things we proved is that the additivity works when you've got a non-measurable set E2 intersecting all the sets involved. So this is still correct. Whether A2 is measurable or not, it's still correct. So we have that. And that's certainly less than or equal to mu A2. And of course, all of these terms are bigger than 0. In fact, they're bigger than tau times the omega n times the diameter over 2. So these are all, because of this inequality, all of these terms are bigger than 0. Now stare at that for a minute. Notice that means that the collection B prime must be countable. See, if you have any collection of positive numbers, and no matter how many of them you pick, you always get a fixed upper bound like that doesn't change, then that means the thing's countable, right? Obviously. Think about that if you haven't thought about that before. Otherwise, there would be some infinite collection bigger than a fixed number, which would contradict this inequality. So this implies that the set B prime is countable. It's countable. So you can write B prime. That means that we can write B prime. We can just enumerate the 1, x1, B rho 2, x2, etc. like that. Okay, so we can do that. And then we can use this on these guys. Use this inequality on these guys. Now remember that each of these balls satisfies this inequality. This inequality here. So we can use that also on each of the balls in this pairwise disjoint collection. So let's do that. So we have the sum by this, we have the sum J equals 1 up to n mu A2 intersect B rho j xj is is less than or equal to mu a2, and it's bigger than or equal to, using this inequality, as I said, on each of the balls B rho j xj, it's bigger than tau times omega n times the sum j equals 1 up to n rho j to the n. So we have that. And of course that means that this series here is finite. So it implies the series of radii to the nth power is finite. J equals 1 to infinity, rho j to the n is finite. In particular, finite. Okay. And furthermore, we haven't yet used double star, so let's use double star now. Also, double star implies that A minus the union, j equals 1 up to n for any n, B rho j xj, is contained in the 5 times enlargements of the remaining elements. So this is the union j equals n plus 1 to infinity of B 5 times rho j xj. I think we can finish it here. And so in other words, A is contained in the union from j equals 1 up to n of the balls, B rho j xj, together with the union from n plus 1 to infinity of the 5 times enlargements. So, and that tells us that, yes, A is that. Now let's see, I made a mistake there. We're applying this to the set A1, aren't we? So we're applying the vitality. A1 is the set that's covered finally. Here it is here. A1 is the set that's covered finally in this case. So we're applying all this to the set A1, not the set A. So that's A1, and this is A1. Okay. And then let's just think about that. Oh yeah, I forgot we should have thrown in one extra condition on this collection of balls, but that doesn't matter. But we do need it. I actually missed a point here. With x, I should have said with x included in A1 and rho less than delta. Here delta is any positive. Take any delta positive to begin with, right? And then throw that in as a condition. Notice that doesn't change anything here. It still covers finally because actually there's a whole sequence of points of radii tending to 0. So certainly some of them are less than delta. So that's not a problem. So take all our balls of radius less than delta. It doesn't change anything here. So let's do that. And then stare at this. This says that A is covered by these balls. These balls have got diameter 2 rho j, which is less than 2 delta. These balls have got radius 5 rho j, or diameter 10 rho j, which is less than 10 delta. So, oh, right, it probably would have been a bit cleaner if I had said rho over 2 there. Then each of these is diameter less than delta. Diameter of those balls is less than delta, and the diameter of these balls is less than 5 delta. But then think about the definition of Hn. That says that Hn of Hn delta, Hn 5 delta, because the maximum radius here is 5 delta. So Hn 5 delta of A1 is less than or equal to the sum of this sum. So the sum omega n. Remember how Hausdorff size 5 delta measures? You take the diameter of these sets, which is 2 rho j over 2. So you take the radius, rho j to the n. Take that, j equals 1 up to n, plus the, here we're working with these 5 times enlargements, so it's a similar sum, but it goes from j equals n plus 1 to infinity of 5 rho j to the n, omega n. That's just by definition of H5 delta. And now you see this. We've shown that this is a finite sum. This guy is finite, so that means as n tends to infinity, this tail term tends to 0. So the whole thing here tends to the sum j equals 1 to infinity, omega n rho j to the n. But that's, so let's take tau times that, multiply by tau each side. Tau each side. And then we can use this inequality, which says that that's less than or equal to mu a2. So indeed, that's exactly the lemma. Except that we still have one thing to do. We should now let tau tend to t, right? And that gives the required inequality. So let's take a break until 4:30. Maybe at the end, yeah. We can get that at the end if you like. Okay. Oh, yeah. Oh, yeah.
So what's for arbitrary metric space?
Yes.
We define Hausdorff measure, use the Euclidean measure, or what you cannot. So
Well, not exactly. Well, no, not exactly. You just, Hausdorff measures defined in terms of coverings of a certain sets with diameter less than delta.
yeah.
And then it's sort of modeled on the sort of idea that you get from Euclidean space, but it's really just general. It's not really.
That's why I'm asking you.
Yeah.
Press the volume omega.
Yeah.
Omega.
Oh, yes,
n,
yes, I see.
arbitrary.
Yeah, but you shouldn't take that constant omega n too seriously. See, the thing is, it wouldn't change any of the theory if you used any normalizing constant there.
I know, no,
Yeah.
not omega n,
Yeah.
Rn.
Yeah.
Rn. So
Yeah.
I mean, ball is
Yeah,
kind of
yes.
Euclidean ball.
Yes, yes.
So you will replace
Yeah.
that guy by arbitrary, some kind of hyperbolic volume, that kind of.
Yeah, no, and so
So it's
no. The only reason you put the omega n in there is so that Hausdorff n-dimensional measure in Rn agrees with the Lebesgue measure. That's the only reason.
My concern
Yeah.
is not omega n, but
Yeah.
Rn.
Rn, yes.
So if you
Yes.
press, forget what omega n.
Yeah,
Just
okay,
Pay
okay.
attention to some function of R.
Yes.
Say for example hyperbolic kind
Yeah.
of thing.
Mm-hmm.
So it's harmless to replace everything by, because the definition is when radius is quite small, so
Yeah.
something every function should be compatible, that kind of thing, or not.
No,
So replace Rn by hyperbolic, for example.
right. Yeah, I'm not quite. I don't think I'm getting your question. Yeah. Yeah.
Okay, replace Rn
Yeah.
by
So what do you have in mind exactly? Yeah. Yeah.
so volume.
Yeah.
Rho
Yes.
R.
Yes.
Now you sort
Yeah.
of replace it by
Yeah.
Rn.
Yes.
So I want to use the other thing.
Yeah.
So for example, some kind of hyperbolic
Yes. Yeah.
volume of
Yes.
R.
Yes.
Of course,
Yes.
lower.
Yes.
So if we replace this guy by that guy,
Yes.
do we have a similar thing of
Oh,
Hausdorff?
yeah. Yeah, but I don't think that's the way to think of it, because remember, this is defined as the limit as delta goes down
Yeah,
to
that's right.
zero.
That's what I'm asking.
So all things turn out to
okay,
be
okay.
equivalent in
I
that
see.
case. Yeah, that's the idea. So it really, yeah, so the answer is no.
Oh, yeah, that's right, sure.
Yeah, that's the thing. So you're not, if you were taking, the info for all possible coverings, then you would be able to say something about that sort of thing. But here you're taking the limit of coverings of diameter delta, and then all spaces are basically flat. You're scaling it, right? All spaces are basically flat. So
All right, so instead,
at that
maybe
scale, yeah.
instead of
yeah,
Rho R,
yeah.
some number Rn, so this defines the dimension of Hausdorff.
Yeah,
Oh, so in
Yeah,
some sense,
yeah.
some kind of
yeah, yeah,
universal
yeah,
you cannot.
yeah. But you see, the thing is, I'm not saying that you can't use other functions other than rho to the n, right? This is just using the n-dimensional Hausdorff measure is what you get when you use that. In fact, it's important. There are other things. If you look in Federer's book, he has other examples. Yeah,
I
yeah.
think
Oh.
every time I always feel it does not work. Okay.
Okay, thanks.
Yeah, welcome.
Thanks. Yeah, keep that. Okay, so let me give you the proof of the upper density theorem. It's been a while, so let me remind you of what that theorem says. Upper density theorem. So X any metric space. And mu a Borel regular outer measure on X. And take A contained in X subset to be mu measurable and of finite measure. Then the upper density the upper n-dimensional density of mu ax is equal to 0 for hn almost every x in the complement of A. And again, let me remind you, this is just the lim sup as rho goes down to 0 of the ratio B rho x intersect A over the volume of the Euclidean ball. So as I mentioned before, notice a very special case of this is when mu is just a Lebesgue measure in Rn, and the metric space is Rn, and mu is just a Lebesgue measure, then this is a well-known fact. But we'll reprove it here, giving it this proof. In fact, I'll have more to say about that special case in a minute. So we're going to use this comparison lemma in order to give the proof of this. So proof so we're trying to show that this upper density is 0 for hn almost every x. So let's consider the possibility that there are various points where it's bigger than some t, right? So let st for t bigger than 0. So take any t bigger than 0 and let st be the set of x in the complement such that the upper density mu ax is bigger than or equal to t. Okay, so that means that the upper density is bigger than or equal to t for every x in st. Now, we can use this lemma. So the question is how. We could use the lemma, for example, when this is. Let me make one other observation here about this quantity. This is our upper density, or in this case, it's this. Notice that in terms of our new notation that we introduced a little while back, this can be written as lim sup as rho goes down to 0 of the measure restricted to A of the ball, B rho x over omega n rho to the n. That's exactly the same statement, because remember, this restriction is defined exactly by taking the intersection with A, right? So exactly the same thing. So this could be rewritten as the set of x in x minus A such that theta star n mu restricted to A, whole space x bigger than or equal to t, or if you want to write it out, it's actually, let's just write it out, it's the lim sup. No, let's leave it like that. Okay, so that's notation, that's another way to write it. So now we can use this this result. We can use this result. I've got to tell you what A1 and A2 are going to be. So, well, one way you could use this result is to take this to be A1, because we do have theta bigger than or equal to t for everywhere on ST by definition. That's what the definition of ST is. So we could take that to be A1, and we could take x to be A2, whole space to be A2, if you wish. But we can do a little bit better than that. If you take an arbitrary C, take any closed C, any closed set C contained in A. Then notice that x minus A is contained in x minus C, and this is open. It's an open set. So that means that this density doesn't change at all because we're taking points x in A, which is in the complement, which is an open set. This density doesn't change at all if you replace x by the open set x minus C, as long as x is still as it is here in this set A. So this is the set of x in x minus A, such that theta star n, mu restricted to A, of x minus C, x bigger than or equal to t. It's exactly the same thing. Because for sufficiently large balls centered at x don't intersect C. X in x minus A, x in x minus C even. So in particular, x in x minus A implies that there exists some rho 0 with b rho x. B rho 0 x intersects C empty. So it doesn't change the density at all. It just, the small enough balls don't even hit C. So it's the same quantity. So that means we can apply the comparison lemma with A2 equal that guy instead of the whole space. So let's do that. So the comparison lemma implies that measure T times the n-dimensional Hausdorff measure of ST is less than or equal to, now the measure in this case is mu restricted to A, right? It's not mu anymore, it's mu restricted to A. And the set A2 is x minus C. But notice by definition, mu restricted to A just means mu of A intersect that set. So this is the same as mu of A minus C. Now, if you think back, one of the things we proved a couple of lectures ago was for a Borel regular measure, for a finite Borel regular measure, you can take the sup, you can get the measure of any set by taking the sup over closed set, so you can make this as small as you like for suitable closed C. Remember, we proved that mu Borel regular finite. In fact, we had a bit more general condition. We allowed it to be open sigma finite, actually, which is a bit more general. But for finite measures in particular, Borel regular finite implies that mu A equals sup over C contained in A of mu C if A is mu measurable, which it is in this case. By the way, don't worry about the finiteness. We're not assuming that mu is finite, but I can rewrite this sort of artificially as mu restricted to A. And that's a finite Borel regular outer measure. So this result is applicable to this. So that means that if we take this, we can make as small as we like. So that means that this guy has got measure 0. We can do this for every epsilon bigger than 0. Repeat this argument. So that means that mu st is equal to 0 for every t bigger than 0. Well, here's st. And notice that what we're really interested in is proving that you can't have positivity, not just bigger than or equal to t, but positivity. So let's think about that. So notice that the set of x in x minus A such that the density is actually positive. Strictly positive can be written as the union I equals 1 to infinity of these sets with t equals 1 over I. Because if it's positive, then it's bigger than 1 over I for some I, right? So, but then we just proved these, so this, we've just proved that is a set of measure 0. So this is a countable union of sets of measure 0. So this equals a set of mu measure 0. So that's it. That's the upper density theorem. Very nice. So we had to struggle a little bit to prove that, but it's a deep result. You expect not to get it too cheaply. So we're going to make rather strong use of that in various places in our later discussion. But for the moment, let me give you one corollary. As I mentioned, there's a corollary involving Lebesgue measure here. So one of the classic theorems about Lebesgue measure that if A is a subset of Rn is Lebesgue measurable, Ln measurable, then the density. Remember, you talk about the density if the upper and lower densities are equal. Then you can talk about density. That's defined to be the common value of the two if they're equal. And the claim is that the common value of the two is the same. And ln a x equals 1 for ln almost every x in A. And it's equal to 0 for ln almost every x in the complement. I claim that's an easy consequence of this general upper density theorem, so let's check that. Okay, let's take any ball and observe that the Lebesgue measure of the ball can be written as the Lebesgue measure of the ball intersect A plus the Lebesgue measure of the ball minus A. And by the upper density theorem, this bit tends to 0 for ln almost every x in the complement of A. Oh, sorry. I forgot to divide by, sorry, I was supposed to be talking about densities. Of course that tends to 0. That's not very hard to prove. It's the measure of a ball of radius rho. No, I'm talking about the ratio. Now, so we're supposed to be dividing by omega n rho to the n. We're supposed to be talking about densities. Omega n rho to the n. There we go. Now this side, of course, is just 1, right? For every rho. So you get that identity. And now this bit tends to, by the upper density theorem, this bit tends to 0 for ln almost every x in the complement. But you see, that's good because that means this side's 1, this is tending to 0, so that's tending to 1. And conversely, this tends to, by the same upper density theorem applied to the complement of A, this bit tends to 0 for almost every x, so this bit tends to 1 for almost every x in A. So you get this. No problem. Yes? Let's see. This is for almost every x in the complement of A, though. Not in this. So this, we showed this tends to 0. This tends to 1 for almost every x in the this bit tends to 1 for almost every x in the complement. Then you apply the same argument with the complement in place of that. So this bit tends to 0 for almost every x in A, and this bit tends to 1 for almost every x in A. So either way, you get this result. So there's nothing extra. It's a trivial consequence of the upper density theorem.
It's 0 for complement, so you apply for the complement, right?
Say that again?
No, I'm saying because the proof is for the complement, so
Yeah, I should have said for the complement, right. So I should have said, no, that's right. This bit, this bit tends, so literally applying that, you should work with this first, tending to 0. But then you can apply it to the complement, and then this bit tends to 0, so this bit tends to 1 in that case. Yeah, so that's it. Very nice conclusion. Okay, so that's the corollary. Now we're almost at the point of, we've almost finished the necessary preliminaries from chapter 1, which I think means we're about on schedule. But there's one more important result I need to talk about. It's called Lusin's theorem, very important theorem, which you may have seen before, depending on what sort of course in measure theory you've seen. Oh, yes, I forgot to mention. Okay, so it's already posted on the web page, so let me remind you again. So the web page is math.stanford.edu/twiddle LMS, it's my initials, /NTU, and there you'll find the latest version of the text. By the way, the text gets updated regularly. You can always see when the latest version has been updated by looking at the bottom of the preface page. It'll always tell you when the update was made. So, for instance, the latest update was made sometime this morning. And the text there's an axiom: you can never find all the errors. You can find most of them, but not all of them. So that you'll find the text on this web page, the latest version of the text, and also you'll find the next week 2 assignment is there. And you'll also find later today, you'll also find the solutions of week 1 assignment. In case you want to check out whether your method of proof was the same as my method of proof. Okay, and the problems for this week, week 2 assignment, for this week, I'm assigning problems 1.2, 2.1, and 2.4. 1.2 is a fairly quickie. It's quite short, but the other 2 are a little bit longer. Okay, so now let's see, Lusin, right. So let's talk about Lusin. Lusin's theorem. So X is any metric space. Mu Borel regular, outer measure. And A, any subset of X which is mu measurable with finite measure. And finally, F is a mapping from A into the reals, a mu measurable map. Then, for every epsilon positive, there exists a closed set C contained in A with mu A minus C less than epsilon. So C chews up most of A, just leaves a little bit of measure left. And F restricted to C continuous. Very nice theorem. It says that any measurable function, as long as you throw away a set of small measure, then what's left is, if you restrict F to what's left, as long as you pick the right set to throw away, then you can arrange that F restricted to the remaining part of the set is a continuous function. Very useful. We'll make use of it from time to time in these lectures. So proof let Aij, so for j equals 0 plus or minus 1 plus or minus 2 and so on, and for I equals 1, 2, etc., let Aij be the pre-image of the half-open interval going from j minus 1 over I up to j over I. Notice it's open on the right end and closed on the left, or you could do it either way around, but the point is it's a half-open interval. Now observe that these are all measurable subsets of A because F is a measurable function, and that's just the definition of measurable functions. You take any interval, take the pre-image of any interval, that's a measurable set. That's the definition of measurable function. So, so these are measurable, mu measurable. Yep, I said that. Mu measurable. And notice that the union over J, for fixed I, the union over J, as you take the union over J, this covers the whole line, right? And these are pairwise disjoint because these intervals don't overlap. So this is, the union over J equals J equals minus infinity to infinity of Aij is equal to the whole set A. And this is a pairwise disjoint union. Disjoint union, because these intervals don't overlap. Okay, so now we've got to think back now to our discussion of Borel regular measures. Remember, we can always approximate this from inside. This is a measurable set, so we can approximate it from inside by closed sets. So so there exists a closed set Cij contained in Aij with the measure of Aij minus Cij less than epsilon. Or we can even do better. I can make it as small as I like. Remember, this is this result again. That here it is. This guy. Same result. So I can make it less than epsilon over 2 to the I plus mod j. Be careful. J is J is going over all the integers, including the negative integers. So you want to put an absolute value there. Plus 2, just to make sure we get the right arithmetic working out at the end. So we can certainly do that, right? And then you look at A minus the measure of A minus the union j equals 1 to infinity Cij. Okay, well that's certainly less than or equal to the, well, it's equal to the mu of the union k equals 1 to infinity aik, because the union of the aiks is equal to a, you see? So I can replace that a by the union minus the union of the c's, j equals 1 to infinity cij. Notice this is, this is for every I equals 1, 2, etc. And for j equals 0, plus or minus 1, etc., plus or minus 2, and so on. Okay, we can do that. And notice, I think we've done this arithmetic before, that this is certainly less than the union of aik minus cik, because this is the union of all the c's. So if we just throw a lot of them away, we're taking complement. So if we throw a lot away except for the cik, then this is less than or equal to the union k equals 1 to infinity aik minus cik. Certainly less than that, which is, by subadditivity, that's less than the sum of the separate measures. That's good. And then we can use this. Now we're summing over k. Oh, right, I tried not to do that, but I did it, didn't I? This is from minus infinity to infinity. Yep. Now we can use this. So let's think about what's the arithmetic. So what's the sum of epsilon over 2 to the mod j as j goes from minus infinity to infinity? It's 1 plus 1 plus 1, right? The 0 term gives 1. And then the other two terms, j goes from 1 to infinity or minus 1 to infinity, both give 1. So it's 3, actually. So this says less than 3, but we had a 2 to play with, which is 4, right? So it's 3 over 4 is less than 1. So that's less than or equal to just, what's left is epsilon over 2 to the I. So what we proved is that mu, this guy, a minus the union j equals minus infinity to infinity cij is less than or equal to epsilon over 2 to the I for every I equals 1, 2, etc. So that's what you get in the first stage of the argument. Now, in fact, it's strictly less because we had 3/4, didn't we? So that's good. Strictly less. Okay. Now, remember, this is when we if we instead take the limit as n tends to infinity, of course, this is no longer correct then, but this is a decreasing sequence of sets, measurable sets. And one of our theorems is that the limit of that, which is this guy, does give this measure, right? You can take if you take a decreasing sequence of sets of finite measure, remember there was that restriction, but these are all finite measure, then you can get the measure of the intersection, countable intersection, by taking the limit of the finite intersections. So we can rewrite this as the limit as n tends to infinity. J equals minus n to n. It's a decreasing sequence of sets. So limit as n tends to infinity gives strictly less. But that means we can pick some n big enough so that the inequality still holds, right? So there exists some n bigger than 1 such that mu of a minus the union j equals minus n to n cij is still less than epsilon over 2 to the I. And we can do that for each. No, but be careful. This is, n depends on I. You mustn't forget that, or you mustn't make the mistake. That would be a novice mistake to forget that you may have to pick a bigger n if you take a different I, right? So it's like that. So, so we could rewrite this as this union can be, notice this union is the same as the union mod j less than or equal to ni Cij. That's what that union is. Okay, now the nice thing about the finite union compared to the infinite union is that that's still a closed set, you see? It's a closed set for each I. So now let's see, well, I'm now going to tell you what the set C is. I claim that we can take the set C, let C equal the intersection of these sets. Intersection I equals 1 to infinity of the union mod j less than or equal to ni of Cij. It's a closed set, and it's contained in A. Closed. So and furthermore, let's look at measure of A minus C. Well, the measure of A minus C is by De Morgan's laws. That's the same as the sum, same as the union. So it's the measure of the union I equals 1 to infinity of the separate complements. So it's A minus the union mod j less than or equal to ni of Cij. Is that the right number of brackets? Yeah. No. Like that. Okay. And then by subadditivity, we can take this is less than or equal to the sum I equals 1 to infinity of the mu of the separate guys. So mu of A minus the union mod j less than or equal to ni Cij. Like that. And then these guys are less than epsilon over 2 to the I. So they sum up to 1. So this is less than or equal to epsilon times the sum I equals 1 to infinity 1 over 2 to the I, which is equal to epsilon. In fact, it's strictly less than that. So indeed, we've got a C that satisfies at least that bit. We've got a closed C which satisfies that bit. Now, what about this condition? Let's look at that. This is sort of interesting. I'm going to define a sequence of functions now. Let gi C into R be defined by taking G, okay, so yes, Cij, right, J less than or equal to that, so, right, yeah, so this is our set C. So, in fact, let me define a function gi on Cij. G, so define gi of x to be equal to this guy, j over I, if x is in Cij. Now, that means that, notice that, yes, Cij, right. And notice that, and do this for, mod j less than or equal to this guy, ni. So we're interested only in mod j less than or equal to ni, because that's where we've got our, that's how we define our set C. So do that, if x is mod j less than or equal. Now stare at that function for a minute. That gives you a function that's defined on this thing. So gi then actually is well defined on the whole union on this guy. And I claim it's a continuous function. It's a continuous function because it's constant on each Cij and they're closed pairwise disjoint sets. And that's always a continuous function. On a metric space, if you take closed pairwise disjoint sets, take a function which is constant on each of those sets, then that's a continuous function. So, because the complement of the, right. I mean, that what I said is false, actually. But if there's finitely many sets, it's correct, because the complement of the complement of any one of them is the complement of any finite union of them is an open set, which contains the one that you haven't used. So think about it. You'll see that this is continuous. That's a continuous function. Furthermore, notice by construction, fx minus gix is always less than 1 over I, less than or equal to 1 over I. In fact, because, as you see, this is exactly the definition, Cij is contained in that. It's contained in the pre-image. So f only takes the values between here on this set Cij. So, and the value we're talking about is this one at the right endpoint. So it's distance less than or equal to 1 over I in each case. So that's true. But stare at that for a minute. That says exactly that on this intersection, if we now take the intersection, on the intersection, gi is a sequence of continuous functions. So thus, gi restricted to C, which is the intersection of all of these, is, of course, still continuous. It was continuous before you restricted it, so it's still continuous, but it's converging uniformly to F. It converges uniformly, so this is uniform convergence to F restricted to C. But the uniform limit of continuous functions is continuous. So that's, F is continuous. Okay, so that's Lusin's theorem, a really nice theorem, a very, very elegant theorem. So let's see, I think that's as much, in fact, that's all we need from chapter 1. You'll find a lot more interesting material in chapter 1. But this is all the material that we're going to need in the later lectures. So I won't cover any more of chapter 1. So next time we'll talk about Lipschitz functions. In fact, I've got a few minutes today, so let me at least introduce the first topic about Lipschitz functions today. So definition. Here X is a metric space. And let's take 2 metric spaces to begin with, I suppose, to make the most general definition. Then F going from X to Y is Lipschitz. if there exists an L, a real number L, such that the metric distance in y between the image points fx and fy is less than or equal to L times the metric distance back in the domain x between x and y. And that's got to be true for every x and y in the space at x. So that's the definition of Lipschitz. Lipschitz functions turn out to be really important, especially in Euclidean space and on submanifolds of Euclidean space. Now, there's a nice theorem about real value. So in the special case when the image, range is R, so lemma, if f, suppose actually we're going to also, so x metric space, and take a subset A contained in X, and then suppose that F is just defined on A to R is Lipschitz. Notice this definition still applies, it's just that we're thinking of the whole space in this context of the mapping as being A, right? You're restricting to A, but Lipschitz definition still applies. Just that instead of x, for every x, y, and x, it's for every x, y, and a. Have that. So Lipschitz. Then the claim is that there exists an extension, a Lipschitz extension f bar going on the whole space. Such that it is an extension. So in other words, f bar restricted to the original set does indeed agree with f. So you can always extend the Lipschitz mapping from a subset. As long as the range is R, you can always extend the Lipschitz mapping from any subset to the whole space. And actually you can use the same Lipschitz constant too. So with Lipschitz constant L, then, if this has got Lipschitz constant L, by the way, this is the smallest thing you can put here is the smallest L, smallest possible L is called the Lipschitz constant. The Lipschitz constant of f. Notice that smallest possible L does exist, right? Just take a sequence that approximates the inf, and you can see that you can use that inf as the constant. Still works here. So this always exists. This makes sense. You can always take the smallest possible L. Still a Lipschitz. Still satisfies this inequality. Okay, so that, in other words, you don't have to increase the Lipschitz constant. You can prove the extension has the same Lipschitz constant. And the proof is fairly straightforward. Let me sort of give you the idea first using a geometric sort of picture. So here's a schematic of the proof. So here's the whole space, and all right, let's be all. Let's use some color, right? And suppose this is the set A. I've been pretty easy on myself. A could be actually very bad, right? It could be very pathological set, but I made it look like just a union of intervals. And then the idea is that you've got your function f here. Let's draw the graph of f. So f is defined above here, so the graph of f. is defined above these guys. And what you do is you take all the possible cones that you can get with vertices, with vertex in this graph. I won't draw any more, but you do that, and then you take the inf of all of those, the inf of the heights of those, and that gives you the extension. So I've got to make that precise now, right? I'm just waffling geometrically, but I've got to make it precise. So the definition of f bar. F bar of y is defined to be the inf taken over x. Take the inf of these. So these are conical things of slope L. So I take, to be precise, I take inf of the values that you get by taking fx plus L times the distance from x to y, such that x is in A. So you see that? That is exactly the analytic way of saying what I'd sketched there geometrically. That's the... And, okay, so there's a little point to check here. It's not quite clear at the moment that this is well defined because we're worried that it might be minus infinity for some points y. So equals minus infinity. We hope not, and in fact it's not. So let's see if we can check that. So fx plus L times dxy, just take any x0 in A, so that can be written as fx0 plus fx minus fx0 plus L times dxy, just for any, take x0, any point, any fixed point. Doesn't matter which one you take. And then notice that this guy is bigger than or equal to minus L times the, by definition of Lipschitz, that's bigger than or equal to minus L times the distance from x to y. So this is bigger than or equal to fx0 minus L times the distance from x to x0 by definition of Lipschitz. So bigger than that, and we still got this term here, plus L times dxy. And then let's see, triangle inequality, dxy minus dxx0 is bigger than or equal to minus dyx0. Did I say that right? Yeah, that's right. By one of the versions of the triangle inequality, that's true. So this is bigger than or equal to fx0 minus d times yx0. And there we go. That's a fixed lower bound. It's bigger than minus infinity. Times L, sorry. So this is at least well defined for each, so that can't happen. That's good. And now we just, well, time's up. So maybe you want to puzzle yourself now to what's still to check. What's still to check is that f bar is a Lipschitz function with the same Lipschitz constant. So why don't you play around with that to see if you can come up with that argument. I'll do it next time. Now we do have to collect the assignment work, right? Yeah.
What kind of target?
Say that?
what kind of attribute Y is.
Ah, yeah. Oh, well, that's an interesting question. Okay, so if Y is Rn, then clearly you can do it just by using each component, but you don't obviously get the same Lipschitz constant then. But